All right, guys. Good afternoon or good morning, whenever you're seeing this recording. Uh, Today I'm gonna go over the forces table lab and the acceleration due to gravity. We're skipping this lab, the interval timers, because there is not really a good simulation in exploration physics for that lab. So these two labs, you are going to need the software. So if you don't have access to it, please let me know or take advantage in working in groups. Some of you have requested not to work in groups, and that's fine. But if you find yourself like you don't have access to a software because software issues, because it might not work in a Mac, just let me know so I can make sure you are working with a group of people, one or two students who have access to a software, and then you guys can, do a Zoom meeting, share screens, maybe meet on campus and work on the lab. Because the idea with this lab is to gather data, just like if you were doing the lab in the building. And you have a few constraints, especially with the free fall motion lab. The force stable lab is actually pretty good. You can even argue that it's as good as the one in person, but the one in person at least gives you a better idea of equilibrium of forces, vector diagrams, trigonometry, and vectors in general, right? You are going to have to do this or to do that in the lab. Like you're going to have to be able to know and recognize a vector, how to break a vector into components. And those are topics that you will be covering in chapter 3 in the lecture. Now, if you need help with any theoretical background in the forces lab, please let me know by email so we can arrange a Zoom or a WebEx meeting, okay? Other than that, lab number 2, you open the software, you go to motion, and then you go into forces, okay? You can mute the sound so you don't have to worry about it. And as you can see, you have here 4 forces acting on a mass. The value of the mass is irrelevant. You are going to be finding the resultant force and the equilibrium force. The force that you have to add to a set of forces so the mass doesn't move. Or maybe moves but very slight. All right, you don't want the mass to move so much. So for example, if I play the simulation, you see the mass moving away from the origin, you don't want that, right? That's why at the beginning, you are going to be given just 2 forces. Ideally, you could make one 90 degrees and the other one at 0 degrees. So then you know that the equilibrium will be around here. Now, the advantages of using the software is that they give you the resultant here of these two. This one is 2.9. This one is 10 newtons. So the resultant is 10.4. So when the instructions ask you for the equilibrium force, the force that will, if I play a simulation, the mass will move like that. You want to find a force, which is this one, that will bring this object to equilibrium. Now, this one is the resultant of these 2 forces. So the resultant of these 2 forces is 10.412 newtons at an angle of 16.2 degrees with respect to the horizontal, of course. So if you think about, right, the force that you have to add, the third force that you will need to add to make sure this object is in equilibrium will be 10.42, well, in this case, okay, so my bad. We have to reduce this. That's fine. That's fine. Let's make this 4.1. You cannot go beyond 10 newtons. That was my mistake. (19°), 0 degrees. So now the resultant is 6.8 and at 37.2 degrees. So this force is the equilibrium force. However, it will not make it 0 yet because of the angle. The resultant force was at 37 degrees here. So you want the angle of this blue force to be 180 plus 37, right? That will be 217. So it was close. Now my net force is 0. If I play a simulation, the mass doesn't move. The mass doesn't move because now you added the equilibrium force, the force that sets the system in equilibrium. All right? That's basically what you have to do in this lab. So let's go to the lab. Let's take a look what you need to focus on. You are going to go to the remote file. You are going to be able to read the objective and the introduction of the lab. Make sure that you understand this because you have to submit 2 files. The theory and the background of the lab, and then your data and calculations. All right, there are 2 files, just like the previous labs. This is all what you're going to cover in the lecture. How to add vectors graphically and the polygon method. And then here you are given the forces and the respective angles you're going to use. So what you need to be careful here is that the forces are given in grams. So you're given the mass, not the force. To find the force, you need to multiply by gravity. Before you have to convert this to kilograms, and then you have to multiply by gravity to find the force in newtons. I will go over that, don't worry. So the first table will take you step by step. Let's suppose, and please let me know which one you use. Some of you may use 1, some of you may use 2, 3. Normally, this is given if this was a remote lab. But because this is an online lab, you guys are going to be able to choose which row you want to use. You're not going to do every row. You are just going to use one of these rows. 1, 2, 3, 4, or 5. Let's suppose you use row 1. 297 grams at 120 degrees. So if you open your calculator, (297 divided by 1,000 multiplied by 9.8), 2.9 newtons. So this is 2.9 newtons at 120 degrees. So you're going to go here, reset this. Oh, 2.9 at 120 degrees. Perfect. And then 125 grams. You convert to kilograms, multiplied by gravity, 1.2 newtons at 195 degrees. There. So if I play the simulation, obviously the mass is going to move, right? So what you need to do is stop it. That's your resultant force, 3.4 newtons at 139 degrees. So you need to find the angle. Imagine you trace a line here, a vector, and then the angle here is 100 and, well, what's 140, right? So the reference angle will be 40 degrees. So it's 40 degrees on the fourth quadrant as well. 360 minus 40 is 320. All right. 3.4 at 320. Aha. As you can see, that's the equilibrium force. 0 newtons is the net force between these three forces. That's why the mass is in. Okay. So how would you fill in the table? You write the weight in grams and the value of the force like I showed you. The same would be the equilibrium force from the force table will be the one that we found. This one. 3.4 newtons at 320 degrees. The math is what you need to do in the resultant theoretical. You need to find the resultant between A and B. For that, you have to use the parallelogram method, where the resultant square is equal to A squared plus B squared minus 2AB times the cosine of the angle in between. Okay? The angle in between, if this is 195 and this is 120, 125 minus 120 is 75 degrees. So that's the angle between the vectors. So you use the parallelogram method, you can find the result, right? Of course, you should know that it's also 3.4 newtons at 140 degrees. All right. Part 2 is simple. You are going to do 300 grams at 0 degrees, 400 grams at 90 degrees. So perpendicular forces, very simple. Okay. The table is identical to table 1. I'm just giving you different forces. All right. The only thing that you need to do for both of these parts is you need to make a vector sketch. The vector sketch should look something like this. Make sure it's legible. And make sure you label the axis here, X and Y, and label each force. All right? If you want to use the one here, it's too small. So this won't help a lot. It will give you an idea, but that's not what I'm looking for. You need to do a vector sketch. All right? The labs are not very long. Once you know what to do, they are very short. So you have time. If you're working in groups, it's even easier. You can divide and conquer. All right? The last experiment is when you are given free forces. So again, you can use 50, 170, and 160. And the procedure is the same. But for that, you're going to use the free force and free angles here, right? So let's say, let's estimate this very quickly. That should be 0.5, I believe. Yes. Yeah. 0.5, 1.7, 1.6. And then the angles, 75, 120, and 340. Yeah. So you have to sketch, but this one is actually very similar. Like here they give you the result of these three forces, and it's supposed to be a 60 degrees. So the equilibrium force will be 1.6. The angle was at 60, 240. There you are. That's your equilibrium for this one here. Now you wonder how I know that very quick. Because the resultant of this free is 1.611 at 61 degrees. So force around here. Well, not totally around here. The angle is 60. If I extend the line of that resultant force, it will give an angle of 60 degrees here. So 180 plus 60 is 240. So that's the angle between the equilibrium force and the x-axis. So you need to complete. You only need to write the equilibrium, the resultant, show the graph, so there's nothing to write here, and the analytical, how you find the analytical. So experimental is what you read from the software. Analytical is doing it on paper. And then you have to do a percentage difference between the experimental and the analytical. All right? Other than that, you have to explain how you do your calculations in table 2, do the percentage difference and discuss about it, and then solve this question. All right? I think that's it for this lab. So I'm going to leave it on forces table for this video because it's quite long already. All right? But expect another video of the free fall to be uploaded soon. That video will help you for lab 4. So the first video I uploaded covers lab 1 and lab 2. This video is about forces lab or forces table. And the next video will be the acceleration due to gravity, the free fall laboratory. And then I will go over the projectile motion and so on. Remember that in between, I will do office hours just in case you have any other questions. All right.